So we're talking about two-slit interference. Last time we kind of got a little bit of the gist, the basic gist, and today we're really going to kind of dive right in. What we have are two slits. We have a wave that's coming in from over here, and that wave that's supplying these, that's arriving at these two slits does so in such a way that you get synced up waves emerging from each slit. So when a crest comes out of one slit, a crest comes out of the other. So they're perfectly synced up. And then the waves that make it through these two slits will observe on the screen what we get. And we'll find that we get constructive and destructive interference depending on how they sync up upon arrival. So let me mark off the center of the screen. So the center of the screen is the point that is exactly, of course, equal distances from each slit. I can't seem to draw it very well because if it should be right about here. And let me go ahead and draw the waves. I drew them as wave fronts before, kind of like the top view of the ripples or whatever. Let me just draw them good old side view at this point, like this. And at the center of the screen, they're definitely going to line up. And the reason why is they're lined up at the source. They're lined up where they emerge from the slits. They travel exactly the same amount of distance. They have the same wavelength, so they're going to line up upon destination. There's no way that they could get out of sync if they just have exactly the same transit distance. But at points over here, that may not be true. So I guess let me just make my thing more clear. Let me erase these. You can re-sketch it if you want. So somewhere over here, if we look at the part of the waves that arrives here, we don't know if they're going to sync up. Even though they're synced up at the source, they may not be synced upon the destination. And the reason why is that they have different travel lengths to get there, and that difference in travel length may actually cause them to be out of sync upon arrival. So what we do, we'll call this transit length L1, we'll call this transit length L2, and the path difference is what we call it. That's the difference in those transit lengths. We'll call that delta L. That'll be L2 minus L1. So that is how different do they, of a journey, what's the difference in the length of the journey they have there. So this is my opportunity to kind of make this a little bit more tangible with a demo. So let's get this fired up. Oh, get this attached here.
Need some help?
Possibly. I don't know why this. Oh, I just need to loosen this clamp a little more. That's the only issue. Okay. So, one thing that you could help with is letting me know if this is showing up on camera. Okay. So here's what I have. These two things here, these are supposed to represent the two slits. These are the two sources of the waves. And notice that I've marked the crests with red dots and the troughs with black dots. And so here, if you can see, I know that this is kind of a budget rate demo here, so I apologize, but there is red dots here. And that, of course, indicates that whatever's coming out of one, coming out of the other. And I just happen to have it as, at the moment, two crests are coming out. But when a crest comes out of one, a crest has to come out of the other, right? So then I go ahead and I look over here. If they have exactly equal transit lengths, so we're somewhere right about here, and we're observing here, you can see that, of course, crest and crest still line up, right? Because they had exactly equal transit lengths to get there. So the center of the screen, the crest and the crest still line up, we get what's called constructive interference, right? So, why is this so shaky?
You might want to move the table a little bit to your left.
To which way? my left this way?
Because where the waves come, it's kind of a little bit cut off. Looks like.
Well, so I think this is where the stupid letterbox mode on this app. I think it was on screen when I first tested it, right? When I have to use another app that actually shows me what the full thing being captured is. This thing is rickety though. That's concerning me.
Because we can see everything to the right, but it's just
because that's just a technical issue. Okay, but you can see this end. Okay, that's the most important thing. So what we can do here is we can ask what happens just above the center of the screen. So right about here. And you notice now that, of course, a crest and a trough are lining up, a red dot and a black dot. And the reason why, of course, it's not that the waves aren't in sync at the beginning, but this one travels slightly shorter and this one travels slightly longer, so there's a path difference. You're going to have to ignore this, of course, because that has no meaning now, because that's past the screen. I can't obviously make these meter sticks shorter for my demo. But the point is that if this screen is here, now the crest and the trough are aligning and they're going to kill each other. So at this point in the screen, we're going to see destructive interference. It's going to be dark. Then let's keep going up on the screen. We go up over here or something. You can see that crest and crest line up again. The transit lengths are different for sure. I've got all this stuff sticking out here because I can't, but I wish I could just chop it off. And the reason why is that even though the transit lengths are different, the transit lengths differ by a whole number of wavelengths. So if you shift one wave with respect to another by a whole number of wavelengths, it's like you didn't shift it at all, right? Basically, whatever relationship they had before, they still have. So you can hopefully see where I'm going with this. If you start from the center of the screen and then go in either direction, you're going to alternately get places where they kill each other, where crest goes on trough, and then other places where they line up again, right? So that's the whole idea. We're going to get alternating constructive and destructive interference going to both sides, okay? Does that make sense? This just keeps going because they go from being out of sync. By the way, how much of a wavelength are they out of sync here if crest lines up with trough? Half a wavelength, right? But when crest lines up with crest again, then they're one full wavelength, right? So that's basically it. If we want to expect constructive interference, we want the path difference to be a full number of wavelengths, right? So that just shifts one wave with respect to another by a whole number of wavelengths, then they still sync up. So I'm going to call that m times lambda, where m can be any integer. M is just the stand-in for any integer value. Okay? So m is just an integer. Alright? So that's my constructive interference. I'll label those with C. And for destructive, we said that they were out of sync by a half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, right? They can be out of sync by 10.5 wavelengths. The 10 wavelengths is just shifting them back with nothing changing, but the half is the important part, right? If you have an extra half in there somewhere, then the half will be the thing that puts crest on the trough and makes them kill each other. So the way I'm going to characterize the destructive interference is like this. Instead of having a separate number in the front that is always half, 1.5, 2.5, 3.5, I'm just going to call that an integer number plus a half. So then I can use the same indexing scheme for both my conditions. So in both of these formulas, m can be any integer. If it obeys this formula, you get constructive. If it obeys this formula, you get destructive. Okay, so again, what we mentioned is that if you go out from the center of the screen, at the center of the screen you'll get a constructive. And that, by the way, is the solution when m is equal to 0. Because notice that if you put m equals 0 into the constructive formula, that produces a path difference of 0. which again means that the distance that both waves traveled was identical. And that's what happens at the center of the screen, right? At the center of the screen, they have the exact same transit lengths, so there is no path difference. Then you'll have destructives on both sides. And that is when the path difference is enough to cause a half a wavelength of offset. That is the m equals 0 solution to this one, right? If you plug in m equals 0 here, you get the path difference is half a wavelength. Okay? But then we noted that you can get to constructive again, right? And this goes out symmetrically on both sides. How much of an offset do they have there? What's the path difference? One full wavelength. Now one travels one full wavelength longer than the other. That's the m equals 1 solution for the constructive formula. And then, of course, there'll be another destructive. And what's the path difference there between the two waves? 1.5 wavelengths. So that's the m equals 1 solution to the destructive formula. And so on and so forth. These will alternate going all the way out. There'll be a pattern of constructive and destructive interference. They just alternate going out this way and going out this way. I should mention, by the way, that if we decide to define the path difference by always subtracting in this order, 2 minus 1, then if we are, this is the center of the screen, anytime we're above the center of the screen, which one is going to be longer, L1 or L2? L2, right? Because you have to travel further to get up there from slit 2 than from slit 1. So there, delta L will be positive because L2 is greater than L1. So when we then go below the center of the screen, of course, one option would be to subtract the things in a different order, or what I'll do is I'll always subtract them in the order 2 minus 1. But if I do that, well, if I'm below the center of the screen, which one of these is longer, L1 or L2? L1. So what that's going to mean is that the delta L will be negative. Of course, they take turns, right? Each one takes turns being the longer one. So if you look at these formulas, you might say, well, if delta L is negative, we don't want a negative wavelength that makes sense. That doesn't make any sense, right? So instead, we just allow m to be negative as well. So m can be any integer, including negative ones. Okay? And that's okay. As long as m is an integer, the plus and the minus is really just a way of bookkeeping which side of the center of the screen we happen to be on. Okay? So that right there is our starting point for understanding why we get the pattern that we do. And I guess before too long, I should probably show you this pattern, and so you believe me that this is what happens when you shoot light through double slit. So here I have a, there's a whole bunch of double slits here. The slits are extremely tiny. And what I'm going to do is I'm going to shoot a laser through it, and let's put it on the screen. So first of all, that is what the laser pointer looks like with just nothing, right? I'm not putting it through two slits. But now I'm going to point this laser. This laser, the dot is wide enough to actually go through both slits here. Let me find some slits. And let me go ahead and point it here. So if I can keep my hand steady, you can see that there is now a series of dots, right? Yes? So there's bright spots alternating with dark spots, right? Now there's obviously some more complicated features which we'll get to in a little bit, but I do want to point out that the basic features there just a series of bright spots and dark spots. Does that make sense? Okay. So, I can't remember if this semester you're going to do this lab, but just in case not, I wanted to show it to you. This is actually part of your the lab equipment. So we get these spots where it's constructive, where the waves are lining up, and other spots where they cancel each other out and it's destructive. Okay. From here, we're going to kind of just delve down into the system and make some approximations here that are very highly accurate for the system and actually makes it easier to work with. Now, in general, the path difference can be tricky to compute. It requires some geometry or something like that. It requires you to actually measure how far is this, how far is this. Finding these lengths is not, generally speaking, very, it requires a little bit of thought. And then once you have each of the path lengths, then you take the difference. And if that difference is a whole number of wavelengths, you'll get a constructive interference there. And if the path difference is a whole number of wavelengths plus an extra half of the wavelengths you're working with, then you'll get a destructive. But what I want to do now is show you that there's actually a trick to make your life easier and just say what the path difference is. So this is going to be the first of two approximations we make that make this system a lot easier to work with. We don't have to compute the path difference on a case-by-case basis. Okay? So approximation number 1, and I should say it's number 1 out of 2. So in both of these approximations, I want to write down what are we conceptually doing, how does that manifest itself as mathematics, and why do we do it? So let me go ahead and sketch the system here again. And we're going to have to start talking about some of the other features of this thing. The one thing I want to talk about is the slit separation. I'll call that D. So how far are the slits apart? I want to also label capital L, that's the distance from the slits to the screen. And my first approximation is going to be that L is much, much greater than D. So the distance from the slits to the screen, far, far, far larger than the slit separation. That was certainly true for my demo just now. The slits are like so close together, they're like the width of a human hair apart. If you look here, they're extremely close together. And that is tiny compared to the distance from the slits to the screen, which in my case was the whiteboard, right? I observed the pattern on the whiteboard. So, if I assume that, and again, I'll answer why would I do that, the upshot of that is that if I were to try to draw this to scale, and this is a tough thing to draw to scale because these are so vastly different. So there are two slits. You may not be able to see the two slits now unless you're in the front row because they're that close together. And then way, way, way over here, I have the observation screen. So I have a tiny slit separation and that's D, and a very, very large observation distance. Even that doesn't do it justice because these are so vastly different in scale that it's really hard to make a drawing. Now, what does that mean? Well, it means if I'm some point over here on the screen asking what's going on, the two waves that arrived, so this one and this one, are very, very close to parallel. Now, obviously they can't be perfectly parallel because they would never meet, right? They come from different places. They come from, one comes from one slit, one comes from the other, and if they were truly parallel, they would never meet. But they are very close to being parallel, right? So if you and a friend start walking in a straight line, and you're slightly different, start in slightly different places, but you meet, 3,000 miles away, or you say you can still see each other 3,000 miles away, you pretty much had a parallel trajectory, right? If after traveling a vast distance, you are still basically in the same place, then you basically have almost had the same trajectory, right? Okay? So conceptually, what does this approximation does for us? It takes that the waves that are interfering at any given point in the screen are approximately parallel. Okay? So that's the concept behind what's going on. Now, if we can assume that, then computing the path difference is actually quite straightforward. So we don't have some kind of crazy one wave coming from over here, another one coming from over here. We have two waves that are basically tracking together. And we can actually, there's a shortcut for quantifying the path difference. Let me tell you what it is. So oftentimes what we also do is we define an angle theta. That angle theta is basically how angled are these two rays from the midline, okay? So if you imagine drawing a line straight from the slits to the center of the screen, how different are the two from that? Now again, you might wonder, aren't they slightly different angles? Yes, they're slightly different angles, otherwise they can never meet, but we're going to approximate that they're about the same, okay? We're approximating that they're parallel, and if they're approximately parallel, then the angle they both go out with is roughly the same, okay? All right, well now what? Let's take a super mega zoomed in view of what's going on at the slits. So we're zooming down here. Remember that the slits are very, very close together, so we're going to have to do a super mega zoomed in view. And what is it going to look like? It's going to look like this. So first of all, let me, of course, draw the slits much further apart because I'm zoomed in. And I'm going to draw the two light rays basically going out in parallel. Now, again, they're not truly in parallel. They ever so slowly come together until very, very far away they finally meet. But in my case, I'm going to say that this angle's theta, and so is this. Okay, well, so what? Oh, and I guess let me label the D, right? D is the slit separation. So one of the things I can do here is I can drop a perpendicular on my thing from one light ray to the other, something like this. So what does that do for me? Well, here's my point. Let's say I had a crest coming out of this slit at this moment. And let's say that I also had, oh, this is where the perpendicular marker gets awkward. Let me erase it for a second. Let's say I also happen to have a crest for this. Well, whatever relationship these two waves have at this moment, they're going to maintain all the way down the line to the screen. So if the crest lines up with the crest here, well, we're going to find later that the crest lines up with the crest, right? So if the two waves line up at this point, here versus here, it will line up down at the screen. Does that make sense? So my whole point here is to be able to show you that right here, that's where all the action is. That'll be the path difference. That'll be how much extra does one travel more than the other. This will be delta L. I didn't want to draw in that bracket because that's going to be annoying. Make things too crowded. So that's delta L. All the path difference is created right there. Okay? So however much one wave travels more than the other, it's all right there. So for instance, if you fit a whole number of wavelengths into that path difference like this, that's one full wavelength, then they'll line up. They'll line up at this location where the dots are, and then they'll line up all the way on down the line at the screen as well. So that's the path difference. It's all right there. And we can use geometry to figure it out by pointing out that this triangle right here, I guess let me try to outline it so it's a little clearer. This triangle right here, this is a right triangle. I guess let me re-sketch it over here. So that's my right triangle. This is delta L, that's where the path difference is made. This is D. And can anyone see what this angle is here? Well, if this angle is theta, right, what's this angle right here? If this is theta, this is 90 minus theta. And then what's this angle?
Theta.
Theta. So this is theta. And so now we just use good old SOHCAHTOA here. And I will point out that the delta L is approximately equal to d sine theta, to the extent that, of course, these things aren't really truly parallel, but close enough. So this is an amazing shortcut because it allows us to find what's the path difference in terms of d, which is the fixed slit separation, and then theta, which is just what angle are we from on the center line on the screen. So the manifestation of the math here is that we can plug in delta L is d sine theta. It's a very quick way to figure out the path difference. Now, why do we do this? Okay, well, one of the reasons, of course, is that it makes it easier to just find the path difference, but it also assumes that the light rays are approximately parallel, and they might not be. The approximation hinges on that. So why do we only look at parallel rays? Why do we only look at cases where L is much, much greater than D? Well, why? It is necessary to see the pattern with visible light with your naked eye. We focus on visible light. I obviously showed you the pattern of visible light. We want to be able to see the pattern without having some kind of instrumentation. We want to just be able to see those alternating bands of bright and dark, constructive and destructive. Now, I have not yet showed you how this follows from this, okay? So that I'm going to reserve for a little bit later. So the connection between why this is, I'm going to do a little bit later. And I'm going to do it after I show you both approximations, so that way I can just kind of do everything all at once. Okay? But for right now, if this is the case, that it's necessary to see the pattern with the visible light with the naked eye, if that's what we're shooting for, if it means doing this, it's a win-win situation, because we get to see what we want to see and somehow make the math easier to do. That's great, right? So we say, hey, we want to limit our situation to being able to see this pattern with visible light, with the naked eye. Okay, well, if that's the case, what kind of mathematical expediency can we gain from this, right? If we're not interested in all patterns and all wavelengths, we're just interested in this particular type of pattern, visible light viewed with the naked eye, why don't we, of course, see what mathematical expediency we can have from that? And this is what results. So, let me go ahead and now use this result. So, I have my equations. For constructive and destructive. This is my constructive. This is my destructive. And all I'm going to do now is plug this in and say this is d sine theta, roughly. And this is d sine theta. So I can solve here and get sine of theta equals m lambda over d, and over here sine of theta equals m plus a half lambda over d. So what do I have here? Well, what I haven't bothered to solve for theta itself because I don't know, I just have something against the inverse sine, I guess, so I'm leaving it as a sine function. But these are a set of angles. I'll call this theta c because these are the angles we're going to find the bright spots at, the constructive interference. So we now have a map of where these things can be found. What angles? If theta equals 0 is the center of the screen, at what angles are we expected to find these features? And then over here we have another list of angles, which I'll call theta dark, or theta destructive. So I now have the ability to find what specific angles these occur at. Okay? So what we, again, remember what we said was, if the center of the screen was theta equals 0, we now have the capability of taking these things where we know we get constructive here, we get destructive here, and they just alternate going to both sides. We now have the ability to find the angles where they're located. So if this is, again, theta equals 0, we can find this angle, we can find this angle, we can find this angle, we can find this angle. Okay? We have the ability now to find the locations, the angular locations of these things, right? So we can say now, if you plug in lambda, which is the wavelength of light you're using, d, which is the slit separation you have, and any integer, and you solve this equation, you'll get the at that angle there will be a constructive spot, right? Etc. Are there any questions on that? Yeah.
So what if it's not a perfect integer? Like, what about the spots between there where they don't either where the crests and troughs don't perfectly line up? Or
right. So there of course is a intermediate ground, right? There's between perfectly lining up and perfectly killing each other. That's where you have what's called partial interference, right? So instead of being perfectly constructive or perfectly destructive. So if you actually look at the brightness pattern is not digital. It's not on, off, on, off, on, off. It does actually vary. So it's not like, if I were to draw it, it's not like on, off, like that, right? That's of course, unrealistic. It looks more like this. So here's what it actually looks like. It's more like this. So there will be parts where they're sort of partially adding up. Now, it's beyond the scope of the class for us to talk about that. So for us, we just talk about where do they perfectly line up and where they perfectly cancel, right? But I'm not going to ask you about any point in between. I got to save some fun for some calculus physics, right? So we're just going to be finding the extreme features, not the points in between. But you're right, of course. You don't go from perfectly lining up to perfectly canceling each other. There's shades of gray in between. So again, it's not really digital, but we're just focused in on the extremes. Okay, so that's my first approximation. Before I move on to the second one, are there any other questions? Okay, so let's do the second one. Let me make sure I fill in the categories the same. Approximation number 2 of 2. So we'll talk about what is the concept behind it, what's the mathematical expediting, and why would we do it? And I'm just going to leave the answer there because the answer is the same. We want to be able to see the pattern with visible light with the naked eye, and that is what is driving both of these approximations. Okay? This idea that we're going to focus on that particular case, and if we focus on that particular case, we might as well use whatever mathematical shortcut might come with it, because if we're not interested in all cases, we're interested in a very specific case, then we can, of course, write down something that would be true for this case, but not in general. So, what is the second approximation? The second approximation is that we look at small angles. So we talked about this map of angles where we see stuff, and we're going to restrict it to only small angles. Okay? So what that means conceptually is that we only are looking near the center of the screen. This one, it's a lot easier to to motivate that this is okay if we're looking at wanting to see the pattern with visible light with the naked eye, because let me again show it to you in case you forgot what it looks like. The pattern looks like this. It does not extend out all the way from wall to wall, right? You can see that the pattern actually fades out, and the total angular width of this thing is maybe a few degrees along the whiteboard, right? So for some reasons yet unknown, the pattern does fade out. So we can really only see the pattern right in the middle, and then once the angle starts to get large, we can't see it with the naked eye anyway. So again, I haven't yet told you why does it fade out, but if it does fade out so we can no longer see it, well, we might as well only look at relatively small angles, right? There's a relatively small angular width where we can see this, so let's use that. Okay? So, what mathematical help might come along with this? This is where we get to use this thing called the small angle approximation. It's a common mathematical trick that is used any time you can be sure that the angle you have, or the angle you care about, is relatively small. We actually used it once in Physics 1 already, when we did simple harmonic motion. So, if you remember, in simple harmonic motion, there was a thing called a pendulum, right? Swung back and forth like this. And it turned out that the pendulum didn't actually play quite nicely with being a system that was easy to work with. And so what we did was we restricted our pendulum oscillations to relatively small angles. And then we could come up with a formula that was highly accurate for the period. In Physics 1, I always have students that then go to lab, and then they start swinging the pendulum like this, and then they say, the formula is not working. It's nothing you're doing wrong, the formula is not supposed to work anymore, okay, because you're not at small angles, okay? So there's nothing you're doing wrong except for expecting a formula that assumes small angles to work when the angle's not small, okay? So what is the mathematical manifestation of this? Well, I guess I'll again briefly show you why this works. So if you plot sine of theta, it has this familiar shape. This, of course, is wiggly shape like this. But if you want to focus in on relatively small angles, so I'll kind of draw myself a little nice band. So I'll kind of sandwich some angles that are relatively close to 0. And I want to point out that this, whatever that line is a really good approximation to sine if you're at small angles. It is, of course, terrible, absolutely terrible out here where this and this are not the same. So, but if you're at small angles, that line will very, very well approximate the sine function. So, a line, what's the equation? Y equals mx plus b, right? But what's the y-intercept of this line? 0. What's being plotted on the y-axis? Sine. What's being plotted on the x-axis? Theta. And I'm also going to have to tell you that the slope of this line is actually 1. So m is actually 1, so what do we get? We get sine of theta is approximately equal to theta for small angles. If you're working with a small angle, sine of theta is pretty much the same as theta itself. If you don't believe me, you can do a quote-unquote experimental proof, or experimental evidence. Take your calculator, put in a very, very small number, hit the sine key, and coming right back at you is basically the same number, okay? I don't know if that's experimental evidence so much. Maybe there's a vast conspiracy where calculators will fool you. But I assure you that at small angles, sine of theta is approximately equal to theta. You can also do one of these for cosine if you want. For cosine, of course, of theta looks like this. Good old cosine, which hopefully you've seen before. And if you sandwich yourself a nice little small range of angles around 0, this right here is a great approximation for cosine. It's a flat line, so how much slope does it have? What's the slope of a flat line? 0. What's this y-intercept? What does cosine peak at? 1. So small angles, cosine of theta is approximately equal to 1. And again, if you want some experimental evidence and or to discover the vast worldwide conspiracy for calculators, okay, put in any small angle, hit the cosine key, and you'll get back basically 1, just a little shy maybe. Okay. So, what does that mean about tangent? Well, tangent is, of course, sine over cosine. So if sine of theta is approximately equal to theta, and cosine of theta is approximately equal to 1, then tan of theta is approximately equal to theta as well. Now, a lot of this is perhaps mathematical stuff that you don't need to know. If you've taken calculus at any point, has anyone taken calculus? Okay, did they talk about something called the Taylor series? Anyone ever heard of that? Okay, getting a couple nods. Okay, these are the first terms of the Taylor series expansion. If you for these functions, if that means anything to you, otherwise, don't worry about it. But what I'm going to do is something that if I didn't justify it somewhat, you would think I was insane. What I'm going to do is going to replace the sine with a tan. So for me, there's no difference between a sine and a tan. So I'm going to use a seemingly totally insane statement that I can, if I'm at small angles, I can replace a sine with a tan with impunity, even though, of course, that would generally be very, very wrong, okay? Because obviously sine and tan are different things. At small angles, though, they start to be very similar. So, why do I want to do that? Let me show you. Have any questions before I take a quick check? Okay. So, let me go back to my diagram. I wish I had it still on the board, but I'm going to redraw it again, I guess. I have my two slits, slit separation D. I have my screen over here, distance capital L away. I have basically two lights going out, light beams going out there. They both have an angle theta, approximately. So, here's what I'm going to do. Maybe instead of characterizing where these constructive and destructive spots are by angular location, right, giving the angles, let me just talk about physical distance in meters along the screen. So let me call this y. So maybe I just want a map of what are the y values that I see these, right? I'll call the center of the screen y equals 0, and then I want to know how many meters, not what angle, but how many meters from the center do I get what features. So I can do the geometry here. This is basically a right triangle, right? So I can say that tan of theta is opposite over adjacent y over L. And this is my relationship that allows me to jump back and forth between the angle and the distance, right? So that equation allows me to say, well, if I'm at such and such an angle, this is my physical distance along the screen. But of course the problem is you have a tan there, and I have a sine in my original function. So this is where I just replace one with the other and just keep going. So what I do is I take this, which is the tan of theta, and I put it in for the sine of theta over here, and it allows me to convert my formulas from where can I find these things as functions of angle to where can I find these things as functions of y, distance along the screen. So that's where my second approximation comes in. My second approximation, let me say that this is y over L. Y over L, okay? It's a nutty maneuver, I know, but it is valid at small angles. It's not valid at other angles, but remember the pattern is disappeared already, so we don't care at large angles. It's true at small angles, and that's all we want. I'll call this y of the constructives and y of the destructives, right? These will be the actual physical locations along the screen I find these, and I can write down my equations. The y values where I'll find the constructives are going to be m lambda L over d, and the y values where I find the destructives is 1 plus a half lambda L over d. And now, I'm going to call it good, no more approximations, because I have exactly what I was seeking. My end goal was to find some kind of physical distance where I can find these features, okay? Okay? At this point, I have used these two approximations. The first one made it easy for me to find the path difference. It allowed me to say where are these things just as a function of angle from the center of the screen, and then the second approximation swooped in and allowed me to change that from what is the angular location of these things to what is the actual physical distance in meters from the center of the screen. At this point, I can just go ahead and draw it. So I want to draw, we of course know to hit this pattern of brights and darks here. And it's a good opportunity to graph it and put a little more detail into the features. Okay? Now again, I have yet to show you why this is necessary for us to see the pattern with the naked eye. I'll show you that again a little bit later, but for right now, let's draw what is this pattern. What does it really look like? Any questions before I do that? Okay, so let's make a little graph. Let me take this pattern and, of course, flip it so that I can put, as usual, the independent variable on the axis like this. So this will be a graph of what intensity do we see on the screen versus distance along the screen, which is, I'll call the y direction. Y equals 0 is the center of the screen. And we already have said that we're going to get maximum intensity there. And then it's going to go to destructive and then constructive, destructive, constructive. So the dots indicate the spots where it's maximally constructive, and the X's are where they're maximally destructive. And I should probably draw it on the other side as well. And it just goes on in both directions. That should be plenty. All right. So we already said that that's what it looked like. Again, as the question was asked earlier, what happens in between? Of course, there's gray area where it's not perfectly constructive or destructive. But our formulas will at least find these extremes. And now we have a way to find them. So what we do is we just go ahead and plug in our m values. If you plug in any integer here, it'll give you the y location of a constructive. So the first one, m equals 0, that gives us y equals 0. So we should expect a constructive at the center of the screen, y equals 0, which we kind of already knew. And the next one, m equals 1, that will be this one. That will occur at lambda L over d. So this right here is the m equals +1 bright, or constructive. This is the m equals 0. This is the m equals +2, 1. And again, remember what's happening there. This is where the path difference is 2 whole wavelengths, right? So they're offset by 2 wavelengths now, which means that they will still line up. And we have been able to, with our 2 approximations, be able to predict what y location are they offset by 2 wavelengths. So you plug in here, you put in m equals 2, and you'll get lambda L over d times 2. So this one occurs at 2 lambda L over d. We can do some of the brights over here, our constructives. M equals -1 is this one. That occurs at y equals negative lambda L over d. And then this one is the m equals -2. That occurs at -2 lambda L over d. So notice that the pattern is perfectly regular, right? Alternating. The spacing is equal. And before we go too long, we should actually probably put in some of the dark ones too, right? So the destructive, if we plug in m equals 0, we'll get 1/2 lambda L over d. That's this one. M equals 0 dark. That gives 1/2 lambda L over d. Notice that that is exactly halfway between the 2 brights or constructives on either side, right? So this pattern is basically totally regular. It's like a ladder, okay? If we plug in, let's say, I don't know, let's start with m equals, let's guys put in m equals 1. So that'll give us 1/2 here, right? So 3/2. This is see m equals plus 1. That'll be 3/2 lambda L over D, which again is halfway between the two adjacent constructives. What have we? That's the m equals 0 and 1. Let's go to -1. So if we put in -1, we'll get -1 plus 1/2, so that's -1/2. So we see that there's a perfect symmetry. The first darks on either side are exactly the same distance from the center. If you're worried about the fact that the m values are asymmetric, 0 and -1, I should point out that m equals 0 is going to have to be one side or the other. But when you plug them in, the actual physical y values come out to be perfectly symmetric. In some books, they have a minus sign here instead of a plus. The only thing that changes is the cataloging of which one has which m value, but all of the actual physical y values come out to be the same. So I don't want you to get too obsessed of thinking like the m values are important. The m values are just a means to get the y values, which is of course what we would measure in the real world. Okay? So it's a little bit good to understand the cataloging of the m values, but that's not the takeaway here. Okay? The takeaway is that the constructives and destructives come out with a regular spacing. Okay? Question?
So as it got further out from the center, though, it got dimmer and dimmer.
Yes, it did.
Are we not looking at where it starts to dim? Or?
Not yet. Yeah. So that'll come a little bit later. But yeah, as far as these equations go, these equations, of course, assume already that the angle has to be small. So this is not really going to be accurate once you get to large y values. So they, of course, the equations, you have to remember that in your head that these equations aren't good forever, right? There's something that happens later on that these equations don't acknowledge. So the thing that I want to point out, and this is actually going to help me to understand the first of my two approximations, this pattern is extremely regular. If I talk about the distance between any two adjacent bright spots or constructive spots, the distance between them, which I'll call delta y, is going to be lambda L over D. If I talk about the separation between any two adjacent dark spots, so say here to here, it's also that. It's very regular. So I'm going to call delta y here, this is the distance along the screen between any two adjacent like spots. So if you're talking about a constructive spot to the next constructive spot, or you're talking about a destructive spot to the next destructive spot, this is your friend, this formula. Just don't forget it's between adjacent like spots. The distance between a bright and the next dark is actually half of this, right? So the brights and darks alternate. Now, if this is the distance along the screen of any two adjacent like spots, this is also an excellent proxy for the spread of the pattern. So I'm going to call this quantity the spread. Because if I know the spacing between any two like spots, well, that spacing is maintained throughout the pattern. So if delta y is smaller, the pattern is going to look like this. And if delta y is larger, the whole pattern is going to look more spread out, right? So here's the thing to understand. If the pattern is too smushed, your eye can no longer tell that there are brights and darks. If a bunch of brights get too close together, your eye just merges them and you can't tell that there's a dark in between, right? In order to see this pattern with the naked eye, you have to have a decent amount of spread, okay? So we need to see with the naked eye delta y needs to be large enough. Okay? So remember, that was our goal, right? We want to see with the naked eye. And so we're going to have to make sure that this pattern isn't totally jammed up with the brights all basically so close to each other that we can't tell that there's a dark in between. So let's take a look at what it does. What is necessary in order for us to see this pattern? Well, we go to the formula for our spread, and let me group it like this. I'm not going to have enough room, so let me bounce over here. Let me just recopy it. So this is basically a measure of the spread of the pattern. And let me look at this for various waves. Sound and light. Light is, of course, what I'm up to right now, but I might be interested in talking about it as well as sound. Okay. So for sound, let's take a typical sound. So I always pull out 440 hertz for sound. That's the middle A on a piano. So that's kind of my baseline for not too high of a note, not too low note. It's basically kind of a very middling kind of sound frequency. The speed of sound is, of course, in air is 343 meters per second. So we get a wavelength for that. If I can compute correctly with d equals f lambda, I will get a wavelength, which is, of course, v over f, which is about 0.8 meters. Okay? So just close enough for, I'll say that's roughly on the order of 1 meter. Okay? Close enough for horseshoes and hand grenades, right? Okay? So if I'm just generally looking, I don't need to worry about it, it's 0.8. It's around 1 meter, okay? Well, if I go to my formula, and the wavelength is on the order of 1, then if the ratio of L over D is also about 1, then I'll get a spread of 1 meter, roughly, right? So again, just really approximate, right? The squiggle means sort of ish. Not even approximately equal to, but sort of, kind of, generally in the right power of 10, okay? Now, you can definitely make out a spread of a pattern that is about 1 meter, okay? And let me show you how you might utilize this when you're talking about interference of sound. So instead of having 2 slits, oftentimes in a stereo you have 2 speakers, right? So you have one speaker and you have another speaker. So those are your 2 slits, right? And what you hope is that the music coming out of them is in sync, okay? So if you play, for instance, a pure tone, you want it to come out crest coming out of one, crest coming out of the other. If you're setting up your stereo, one of the mistakes you can make is to have them out of phase. That's if you put the 2 wires reverse. So has anyone ever set up a stereo? Got to put in the speaker wires, put 2 of them on each speaker. Don't reverse them, because then you get a phase issue. So what you want to do is make sure that when a crest comes out of one, crest comes out of the other, not a trough. So what you do if you're a true audiophile is you set yourself up so that you are exactly equidistant from your speakers when you are trying to get your maximum audio experience, right? So we can call this constructed, right? So you can, jockey for your spot on the couch and not get, a seat right next to here where you might actually get some destructive, okay? Where the path difference starts to be so that they will not sync up anymore. And we've just shown that that spread of the pattern from here to the next constructive, that's about 1 meter. So obviously 1 meter is plenty to be able to tell the brights from the darks. Well, or in this case, of course, the louds from the quiets. Now, I'm not saying that if you play a pure tone in your stereo speakers, that you can literally move your head from the middle of your speakers, hear and then have it just turn off because they're killing each other. That's obviously not realistic. Why is that? Number one, you have two ears. So one ear might be in where they cancel, but the other one is not. The other reason, sound bounces off walls, so you're not getting everything directly from the speakers. Okay? Another reason is that you probably don't listen to music that sounds like It has lots of different wavelengths, right? And the different wavelengths all have the different spreads. Okay? So, but you might hear that as you move away, the sound isn't quite as full or rich. And that's, of course, why you want to set it up so that you are equidistant from the speakers. Because if you're equidistant from the speakers, all wavelengths will constructively interfere here. Okay? So that's a little bit about, this works also with stereo speakers. But we're focused in on light. So light, let me remind you, has a much, much smaller frequency. So for instance, light, a typical wavelength that we might talk about, let me just jump straight to wavelength. Let's take a wavelength of 500 nanometers. So that's a vacuum wavelength, pretty much the same in air. That's somewhere right in the middle of the vacuum wavelengths for visible light, right? 400 to 700 nanometers. Incredibly small. So if we're just talking close enough, we're talking on the order of nanometers, right? So what do we have to do? Well, think about it like this. We have a tiny, tiny wavelength. And that would, in this spread equation, tend to jeopardize the spread of the pattern, right? It would tend to make it very, very low. Because if the wavelength is low, then the spread is going to be low. And we're in danger of having the pattern be too smushed for us to be able to tell it's there. So we're going to have to somehow compensate for that over here, right? So what do we want to do to L over D?
L bigger and D smaller.
We want L bigger and D smaller. We want this ratio to be very large, right? So big L, small d. That, to combat the fact that we have a tiny wavelength, we're going to have that this ratio is very large so that the delta y might be big enough to be able to see the pattern. Okay? So it's not that the pattern doesn't exist otherwise. And you don't need to go to these extreme measures when you're talking about other waves, right? If you look at sound waves, there's no way that these sound waves are parallel at all, right? But if you're talking about light, the wavelength is so small that you have to do something to make up for that to be able to get this pattern to spread out enough, and that, of course, means that L is going to have to be much, much greater than D, which is our approximation number 1. So this kind of validates that. The only reason we make this approximation is we want to be able to see this pattern with visible light with the naked eye. Okay? So the problem is visible light has an extremely small wavelength. So if we still want the pattern to spread out enough to be able to see it with visible light, we're going to have to compensate for that with this. Okay? So this allows a very small wavelength, which is visible light, to have a large enough delta y to see with the naked eye, without any special instrumentation to be able to tell that there are constructives and destructives in there. That's why, of course, we make that approximation. If we want a small wavelength of visible light to show a pattern that's large enough to see, then we might as well make whatever mathematical expediency might come along with that. And we, of course, saw that this leads us also to a very simple formula for path difference. So it's a kind of a win-win. Okay? So that's approximation number one. Okay? That is the tie-in between being able to see it with the naked eye and, of course, the d sine theta business that we then went through. In the second approximation, and this is jumping on the gun a little bit, remember the approximation number 2 was small angle. So again, the reason why we made that is because we want to be able to see the pattern with visible light, with the naked eye. So the question then is, what is it that kills that pattern anyway for larger angles? I'm going to jump the gun and kind of tell you what the next topic is that we're going to be talking about. Something called single slit effects kill the pattern for larger angles anyway. So there's another phenomenon, which is our next order of business, and that is why the pattern does fade out after relatively modest angles. And so if those effects, whatever those are, kill the pattern anyway, let's go ahead and use whatever mathematical expedients might come with small angle. Namely, we can set a sine equal to a tangent and just keep on barreling through, okay, instead of having to do something more complicated. Okay, so that should do it for today. That should do it for the single slit, or sorry, the double slit or two-slit interference. We'll do the single slit stuff next time.